Hi, my name is Kim Davies. I'm the Director of Technical Services here at ICANN, and part of my responsibility is managing aspects of the domain name functions within the IANA. So in this section, I'm going to talk to you about the domain name functions within the IANA. Just as a recap, IANA is typically divided into three different sections. There's protocol parameters, number resources, and domain names. There's different presentations for each of these three sections. We're going to focus on domain names during this section. When we talk about domain names within IANA, it's important to consider that within the whole scope of IANA, we maintain multiple different aspects of the domain name system. For example, we maintain resource record types, security algorithm types, and DNS header flags. These types of allocations that we make on behalf of the domain name system, we handle in the protocol parameters area of the IANA. So when we talk about the domain name functions within IANA, we're really just focusing on what we call the domain name space, which I'll explain in a moment. The domain name space refers to the domain names themselves, those addresses that we use on the internet to navigate to locations online. If you break apart domain names, they're generally represented as a tree structure. The .org, .us, .bel at the end of a domain, for example. These are what we call top-level domains, and underneath those we have second-level domains, third-level domains, and so on. At the top of this hierarchy is what we call the DNS root zone. This root is the official registry of what top-level domains are in existence, and is one of the primary responsibilities that IANA has for domain name functions. In managing the root zone, we receive requests from TLD operators to perform changes. To do one of those changes, usually there's some kind of triggering event. The operator of a top-level domain might be doing, for example, routine maintenance. Maybe one of their staff members have left the organization. Maybe they're instantiating some new servers that need to be referenced in the root zone. In more rare cases, we see that sometimes there's a natural disaster or some other kind of change that's unexpected, but nonetheless requires some kind of change to be made. Real life examples, we've seen countries experience things like hurricanes, floods, earthquakes, and so on. These have then significantly impacted their internal infrastructure within the country. In order to keep their top-level domain for that country online, or to improve its situation, they've needed to make some changes to move the location of their servers, of their infrastructure to a new location. In the root zone database, we maintain various bits of data that are used to support the top-level domain. Firstly, we have the official record of who is the operator of a given top-level domain. That's the recognized company or organization, including its legal name, physical address, and so on. We have two contact persons for a domain. We have an administrative contact and a technical contact, along with their names, contact details, and so on. We have the technical configuration data for top-level domains. This is the stuff that gets put into the DNS itself, the technical data that makes the DNS function. So for every top-level domain, there's a set of name servers that need to be listed. So we list the authoritative name servers for every top-level domain. There's the IP addresses associated with those name servers, and there's also DNSSEC records used to secure those top-level domains. We also maintain data on various other information, not essential to the operation of the domain, but nonetheless useful for the general community. For example, the URL where you can go to find the operator's website. Perhaps you want to find out how to register a domain within that TLD. The location of the WHOIS service. This is where you find out who has registered a domain within the given TLD. We also have various other bits of metadata as well. Just as a real-life example, here is a snapshot of one of the actual top-level domains, the registry entry for .hamburg. Here you can see the name of the entity that runs the domain, its location. We see the contact persons, both the administrative and technical. And then we see the technical configuration data. This technical configuration data is not necessary for people to read per se, but is required by DNS resolution software in order to make .hamburg actually function. We also have the address to the .hamburg website, its WHOIS server as well. So we have an event that triggers a change to some of that data I just showed you. What's going to happen is that the TLD operator is going to need to submit that change request to us for us to process. We provide an online automated web service where the majority of our customers lodge these kind of change requests. They can log in using a username and password. They can look at their current set of data and they can request changes to what's listed in our database. We also provide other mechanisms such as a 24/7 emergency contact number, so that in those rare cases where there's an emergency, perhaps they lack internet connectivity, there are other mechanisms by which we can receive change requests. But in the normal course of business, we would expect to receive those change requests via this web interface. So we get that request, and it's usually of the form of like change this server, change the address, change the operator of this TLD, or more recently we're seeing a great expansion in the number of top-level domains with a new gTLD program. As a result, we regularly receive requests from gTLD operators to create their new top-level domains. So this gets submitted via this process as well. So we receive a request through our system. Our job is to check that it meets the various policy and technical requirements and to confirm consent from the appropriate parties. There's various policies and procedures that dictate what kinds of changes can be made when. We can't simply accept any kind of data in all those fields. Most importantly, we need to make sure that the technical data that's provided is actually functioning. If we find issues with this, we go back to the requester and we ask them to clarify what the issue is and ask them for an explanation. Usually they'll identify an error or a mistake, go back and fix it, and then we'll attempt to process it again. Consent is another important part here. Changes can be submitted by anyone, but the changes will only go forward if the representatives of the TLD operator consent to the change. So part of our processing is going back to the TLD operator, going back to their designated representatives and asking them to confirm the change should proceed. Once we've done those reviews in terms of making sure it meets the policy and technical requirements, we then submit the request forward for authorization to proceed. Just a little more detail on the kinds of checks that we do. Firstly, technical. I mentioned earlier that there's a list of name servers associated with every top-level domain. We do automated technical tests to make sure those name servers are functioning correctly. We make sure that they actually respond. The responses that we do get back contain the correct data. That data matches what has been requested. We also validate the DNSSEC records. We can do validations on the data return, make sure that that matches as well. For the fields where there's email addresses, we send an email to those email addresses, make sure the email goes through. That's all part of the automated technical testing we do for change requests. I mentioned consent. We make sure that the existing contacts agree to a change. We make sure that any new contacts for the domain agree to their new responsibilities. And then in some specific cases, there's certain kinds of technical changes where a change to one TLD can actually impact other TLDs. So when we identify one of these types of changes, we make sure that the other TLDs that might be impacted by that change also agree for that change to go ahead. We have certain legal requirements associated with performing change requests. So in the course of doing our processing for a change request, we make sure any and all legal requirements have been met. We also check for well-formedness, make sure there's no typos or spelling mistakes in what's being suggested. We make sure that all the data that we're being asked to list is clear, well-formed, and consistent. It's also worth noting that in the very specific case of transferring responsibility for a TLD from one party to another, this has a whole additional set of policy requirements that need to be reviewed and assessed. These policy requirements differ depending on whether it's a country code top-level domain or whether it's a generic top-level domain. So just to explain what that difference is, the GTLDs, we're talking here about .com, .net as some early examples. Newer examples might be .music, .ninja. There's literally hundreds of them. These requests for GTLDs are governed by ICANN's policies and a contracting process associated with that. So whenever there's a change of operation of a GTLD, that will be reflected by a new contract having been executed between the new operator and ICANN. So when the IANA functions receive such a request, what we do is look to make sure that there has been an evaluation and contracting process conducted for either the new TLD or the change of operator, make sure that that has been conducted in association with the GNSO's policies, and that is our evidence to proceed on the basis of the request. Now for CCTLDs it's very different. CCTLDs are largely managed within the countries that they're designated to. So really what we're looking for there is evidence that a consensus building process has been conducted within the country to select the new operator of the TLD. Any request to either assign a new CCTLD or reassign it to a new party needs to provide evidence that a local decision has been made within the country, that the relevant stakeholders have agreed, and that there is consensus to proceed with the change. We do a review of the documentation provided. There's a certain set of criteria against which it's assessed, and assuming it meets that criteria, we proceed with those kinds of changes. So ICANN has done all its processing and it's ready to proceed. The next step is the step of verification. As part of the current contract that ICANN has with the US government, we're required to send all changes to the root zone database to NTIA for verification. NTIA being an agency of the US Department of Commerce. NTIA reviews each change and then gives authorization to proceed with implementing and publishing the change. Finally, once we've received that authorization to proceed, we're ready to go ahead and implement it. For changes that are to the root zone file, those technical data changes, they're implemented in the root zone by VeriSign. And any changes to the root zone database, such as those contact details, the authoritative record of who runs this TLD, that is done by ICANN following that authorization. So part of the management of the root zone is not just maintaining the records that we just talked about, it's also maintaining the security around the root zone using DNSSEC. A key part of DNSSEC is maintenance of what we call the key signing key for the root zone. This is sort of the ultimate master key that protects the root zone and in turn protects all the different DNSSEC signed zones around the world. So part of the root zone management functions is maintaining that key signing key, or we call it the KSK. And we do that by conducting a series of key signing ceremonies. These are public events where we perform transactions involving the KSK. And just to explain what that means, I'll walk through a few diagrams that kind of explain the concept and how the ceremonies are conducted. So the key itself is actually a file. It's a computer file that's used to generate cryptographic signatures. The way we store it in a specialized device known as a hardware security module. A hardware security module's sole purpose is to securely store these keys. This device is designed to be tamper-proof insofar as you can think of it as a very specialized external hard drive for your computer that does some special functions. But what it does is it knows when it's being tampered with. If you try to, for example, try to open it or unscrew it, the device will self-destruct. If the temperature variation around the device is too different, it will self-destruct. There's a variety of different ways that it protects the data within it. So in essence, this box is designed that only when it's accessed in the proper way will it volunteer the information contained within it. but in normal operation, if anyone tries to obtain its contents in an unauthorized fashion, they will not be able to. So we have these specialized devices that store the key signing key, and we have a number of them. And in order to use them in an authorized fashion, there's a set of smart cards that have been created to activate one. The way we've configured them is for each of these HSMs that we have, we've generated 7 smart cards. In order to turn the HSM on, we need 3 of those 7 smart cards to be present in order to make it usable. If we don't have those 3 smart cards, the device simply won't turn on and we cannot use it. So what we've done is we've taken those 7 smart cards and in effect given each one to a different community member from the ICANN broader community. We call these people trusted community representatives. This means that for us to access this device, we need to get 3 of these 7 independent people to come together to turn the device on. These trusted community representatives are from the broader ICANN community. Some of them are technical experts in DNSSEC, some are registry operators, some are well-known members of the community known by TLD members. The point is they've been chosen because they're trusted to perform this process. So it's part of the safeguards that we use to make sure that the key signing key is only used for its intended purpose in a very controlled manner. So we have this specialized device, the HSM, that contains the KSK. As another layer of security, we store it inside a high security safe. Now this safe can only be opened by a designated person, which is called the safe security controller. And this safe is monitored with seismic and other sensors to ensure that no one tries to get in the safe in an unauthorized fashion. Next layer of security for protecting the KSK, we store the safes used for storing the HSMs are stored in a secure room. This room is secured by access control system that requires 2 separate people to be present in order to open the ceremony, open the room. These are known as the ceremony administrator and the internal witness. Again, the room is monitored with a variety of sensors to make sure that no one gets in that room undetected. So this safe room is then secured in another larger room that wraps around it where we actually conduct ceremonies. So we have this larger secured room where in the course of a ceremony we will take the HSM out of the safes, we will take it out of the secure room, we will get those 3 of those 7 community members to activate the HSM, and then we'll perform the functions that are required to secure the root zone. Now access to this whole room is secured by another person that's needed, a physical access control manager who is not on site. So someone that is off-site from the premises needs to coordinate to make sure anyone can get access to this larger room. Whenever we're inside this room, we make sure that everything is recorded on video, that we have third-party participants in the room to witness all the events that happen in the room. And we also engage a third-party audit firm to come in and monitor the ceremonies conducted in the room. I think the important thing to consider looking through all these layers of security is we're really trying to instill trust in the community that the contents of those HSMs, that key signing key, is never compromised in an unauthorized fashion. We have multiple layers of security to provide that assurance to the community that in order to ever access those files, you need many people to coordinate, including these trusted community representatives in the community, and this provides assurance that the key is never compromised and is always maintained in a safe fashion. As part of the resilience of this service, we actually have duplicate sites. Both are mirror images of one another. One is on the west coast of the US, one is on the east coast of the US. In practice, we alternate between the two in terms of when we do our ceremonies. But the thinking there is if there's any event that takes one of those facilities offline, we have the other site available as a backup if needed. So we have these facilities, and inside them is well secured that key signing key. how do we actually put it to use? So we have these ceremonies. We have approximately 4 per year. And so 4 times a year, all the people that are needed to access the KSK coalesce in the location, and that includes the TCRs, those community representatives who fly in from many different countries to participate. We meet at a scheduled time for a ceremony where we open the safe, retrieve the HSM, and we conduct the functions on the HSM that are needed. Generally speaking, we use the HSM to generate one 3-month period worth of signatures that are needed to secure the root zone. So every 3 months we generate 3 months worth, and so doing that 4 times a year keeps us secure. Every time we do this process, it's streamed and recorded, so you can watch online. We have those external witnesses there watching every step as well. And all the materials from the ceremonies, including the videos of it, the source code used to operate the machine, the scripts and so on, are all posted online on our website. Again, the overall purpose here is that through doing it in this fashion in a very deliberate, public manner, it ensures trust in the process. DNSSEC is only useful if the community believes and confirms that the KSK is never compromised, and therefore the signatures generated from the KSK are trusted to be authentic. So here's a photo from a recent key signing ceremony conducted last year. And it's worthwhile noting that we've had a few documentary crews come and monitor our ceremonies in the past. And if a lot of this seems a little too abstract to digest, it might be easy to understand to look at some of these documentaries that are online. We had the Guardian newspaper visit us, and they produced some footage of how the key signing ceremony works. We also had BBC's Horizon show come and produce a documentary on how it works as well. I think it's important to note, just closing this topic, security at IANA is beyond just DNSSEC. While the first thing that comes to mind when we talk about security in the DNS is DNSSEC, it's also worth noting that the workflow systems that IANA uses to support our broader functions have their own security considerations that are an important part of what we do. Some of the measures that we have in place is that the IANA functions have their own dedicated workflow systems. These are independent of the broader systems used across the whole of ICANN. And these systems are limited to only the IANA staff to perform their individual roles. So in the ordinary course of business, staff from other parts of ICANN do not have access to the IANA systems. We also have separation of the user-facing and staff-facing systems so that our customers have access to a certain system. Our staff have access to different systems to perform their particular roles, thus limiting exposure of the different functionality in a way that might be compromised. I think most importantly, we have third-party audits regularly conducted on the way we do these systems and how they operate. So we have PricewaterhouseCoopers conducting an audit of our Internet Registry Management systems. They come in and look at the policies we use to manage these systems. They look at our internal processes. They look for evidence to show that we follow our processes, and that provides important feedback to us and also confidence to the broader community that the controls that we have in place are being used in an effective way. As you would have seen in the other modules, we have a variety of performance reports that we share with the community that demonstrates how we do our job. These include a number of monthly reports showing metrics such as timeliness, accuracy. This is part of the way that the community assesses our performance and provides feedback on how we're meeting their expectations. The current set of KPIs that are used for the reporting were designed in agreement with the community in 2013, and we constantly evolve and seek additional feedback from the community on how to further grow and change our service. Here's another example of some of the metrics that we use in terms of domain name functioning, timeliness, accuracy, on a number of different aspects of how we process change requests. So just to wrap up performance reporting, here is a full 2014 summary of change requests received in terms of domain names by the IANA functions. So on average, we tend to see somewhere between 50 to up to 123 change requests per month. As you can see, we meet our KPIs a bulk of the time. We have certain service level agreements that we've met in 11 of the 12 months. And the average time to process change requests varies. Usually it's in a small number of days. You can find all these stats in more granular detail on the IANA website at iana.org/performance. So this concludes this section of the presentation. If you have any questions about this, please reach out to the IANA staff at the contact